Hello and welcome back to our series on abstract algebra. This is going to be our second video on rings. And if you remember from the first video, we just went through the basic definition of rings. So we saw a ring has to be non-empty, have addition and multiplication operations, and then it has to satisfy these first 8 axioms. Okay? And then if you remember, these 2 extra axioms here, these are extra. A ring isn't required to satisfy these, but a lot of rings do. Okay, and then we also went through and looked at the integers, and we saw how the set of integers satisfied the definition of a ring. And the integers actually also satisfy these 2 properties as well. Now we're going to take a look at some additional examples of rings. So one example we could look at is the set of all even numbers or even integers. Okay, so if you take any 2 even integers, right, like say 4 and 6, and I add them together, right, you see in this case I get 10, and I get another even number. It's not too hard to prove that this will always be the case for any 2 even integers you pick, right? If you take 2 even integers and you add them, you will always get an even integer. So this first criteria is satisfied. The second one, obviously, if addition is associative for the integers, which we already saw last time, it'll be associative for the even integers. Same thing with the commutative property. For this fourth criteria here, this, remember, is the additive identity. Every ring has to have one. For the integers, the additive identity was just the number 0. For the set of even numbers, the additive identity is also 0, right? 2 plus 0 equals 0, 4 plus 0 equals 0, and so on and so forth. So this criteria is satisfied by the number 0. 0 is an even number too. Some people forget that, but yeah. So the number 0 is in this set. Okay. For axiom 5 here, right? Every element in the ring has to have an additive inverse. Okay. For the even numbers, this is pretty easy. 2 is an even number, and -2 is also an even number. If you add these together, you get 0. Okay, so that's satisfied. If you take 2 even numbers and you multiply them together, you will also get an even number, right? It's just an example. 4 times 8 will give you 32, right? The result's even. Again, it's not hard to prove that this will happen with any 2 even numbers that you pick, but we won't do that now. 7, multiplicative is multiplication is going to be associative for even numbers. We already saw before that it's associative for all integers, so it's not going to fail for the even numbers. So 7 holds. Last one, number 8. Basically the same deal here. We already know that all integers obey this distribution property. Okay, so property 8 is also satisfied by the even numbers. So we went through all of them. We showed that all these properties are satisfied by the even numbers. Therefore, the set of even numbers constitutes a ring. Okay. The even numbers also satisfies number 9 here. It's commutative under multiplication. But it does not satisfy 10. Okay? So the even numbers, the set of even numbers, does not have a multiplicative identity. There is no even number, such that if you multiply it by any other even number, you get that second even number back, right? the integers, the set of integers had this because that was the number 1, but 1 is not an even number, so the set of even numbers does not have this multiplicative identity, but it doesn't need it to be a ring. Okay, now we just looked at the even numbers, and you might be wondering, what about the odd numbers? Does the same thing work for the odd numbers? And the answer is no. The odd numbers, the set of odd numbers, does not constitute a ring. And it actually fails a few of these criteria. But just looking at a few of them here, right, if we take any two odd numbers, like say 3 plus 7, we get 10. So look at this. I took an odd number, right? A number in this, well, I forgot to change that. Right? I took a number in this set, and I added it to another number in this set, but I got a number that is not in this set. So with the odd numbers, I was able to escape the ring through addition, right? So we violated this very first axiom here. So just based on that alone, this already fails to be a ring, okay? But it also fails to be a ring in a couple other ways. There's also no additive identity for the odd numbers. Because remember, the number 0 is not an odd number. It's an even number. So 0 isn't in this set. So there is no additive identity for this set. Okay. So the even numbers formed a ring. Now let's look at another example. This time we're going to look at a ring of matrices. Okay, so we're going to look at the set of all 2 by 2 matrices. Okay, so I'm just going to use this notation, right? The set of all 2 by 2 matrices where the elements of the matrix are all real numbers. Okay, so A, B, C, and D are all real numbers, right? This fancy R here denotes the set of real numbers, right? So this is just saying all of these have to be real numbers, okay? And if we're looking at the set of all possible matrices of this form, this forms a ring, okay? Now, in this example, the elements of the ring are no longer numbers, right? The elements of the ring are now matrices, okay? So you remember in the definition of the ring, we never stipulated that the elements had to be numbers. Rings are sort of defined the way they are to make them more abstract so that we can apply them to a wider range of different mathematical objects. Okay, so in this case, we're going to look at a ring where the elements are not numbers, but they're still related to numbers, right? Because these elements of the matrices are still normal real numbers. Okay, now if we're going through these axioms, here something else I should say about this. For this ring, the operations, we still have this idea of addition and multiplication, okay? But the addition here is going to be element by element addition, normal matrix addition, and the multiplication is going to be matrix multiplication, right? So if you remember back when I said these two operations are usually thought of as addition and multiplication, they don't necessarily have to be exactly what you think of as multiplication and addition when you're thinking about multiplying and adding numbers together, like integers, right? In this case, the multiplication operation is going to be matrix multiplication, and the addition operation is matrix addition. Okay, now it's not too hard to verify this first property, right? If I take two matrices where the elements are real numbers, and remember when you add two matrices together, you just add them element by element. Okay, so as an example, you know, if I just make up two matrices really quickly here, right, this addition would look like this. It would be 8, 5, 7, 6. Okay, we get another 2 by 2 matrix where these are all real numbers. Okay, so everything works. Matrix addition is known to be associative. I'm not going to go through it right now, but that works. You could probably see pretty easily that matrix addition is going to be associative, since when we're adding matrices together, we're just adding the elements together, right? It doesn't matter whether this matrix comes first or this one comes first. You're going to get the same thing either way. So addition is commutative with matrices, so it satisfies this criteria. This set has a 0 element, but the 0 element, okay, is not going to be the number 0 anymore. In this case, this 0 element of the ring is going to be what you might call the 0 matrix. It's just going to be this 2 by 2 matrix where every element is 0, right? And you know, you could probably see pretty easily how this would work. If I added this to another matrix, all of the elements are just going to have 0 added to it, and I'm going to get the same matrix that I started with. So in this case, the additive identity is not the number 0 like it was for the integers or the even numbers. Now the additive identity is the 0 matrix. Okay. Every matrix is going to have an additive inverse, right? All I would have to do in this case is just make these elements -1, -2, -3, -4, right? And then when I add these together, I'll get the additive identity matrix. Okay, so this is pretty easy to verify. Matrix, now here's where we get to something a little different. So remember, the multiplication operation here is going to be matrix multiplication. And it is true that if you multiply two matrices together, right, where the elements are all real numbers, the product, the result of that multiplication is going to be another matrix where they're all real numbers. So this works under matrix multiplication. Matrix multiplication is known to be associative. I'm not going to go through and prove that right now, but that's something that you probably would have seen you know, in a high school class that dealt with matrices. And matrix multiplication is known to obey these distributive laws. So yeah, the matrix operations of addition and multiplication work with this. So the matrices, or this set of matrices does constitute a ring because it satisfies all 8 of these requirements. Now, in addition to these 8, this set does also satisfy 10 here, right? Because we do have an identity, a multiplicative identity with this, and that is something called the identity matrix. And if you've studied matrices before, you probably remember what this is. It's this matrix. This is the multiplicative identity for this ring. If you multiply this matrix by any other matrix, you will get that other matrix. In the same way that if you multiply any integer by 1, you get that integer back. So this property is satisfied by this ring, but this one is not. Matrix multiplication is not generally commutative. So this last property 9 here fails. Okay, now all of the matrices, or all of the rings that we've looked at so far have been infinite rings, right? We've looked at the integers, the even numbers, this set of matrices, right? These rings all have an infinite number of elements in them, right? There are an infinite number of integers, an infinite number of even numbers, and so on. Next video, we'll take a look at some important rings that are finite. In other words, they only have a finite number of elements in them. Thank you for watching this video. Let me know down below in the comments if you have any suggestions or questions for future videos.